Hello, this is Carol. This is my presentation on fractals. This is my presentation outline. I want to first talk about a brief introduction on fractals, and then I will discuss how fractals are everywhere in our daily lives. Finally, because I'm a middle school math teacher, I will share some cool classroom activities for students to further explore fractals. So, first of all, what is a fractal? A fractal is an ever-repeating pattern. Every part of a fractal, however tiny it is, looks just similar to the whole image. In other words, when you zoom in to see its details, you can see numerous repetitions. The concept of repetition or self-similarity is pretty simple, but such simplicity can form an indefinitely complex shape eventually. So, in 1975, an unconventional French mathematician, Benoit Mondepro, created the term fractal. So, fractal originated from this Latin word fractus. Fractus means the fragmented or the broken. Here you can see a visualization of the famous Mondepro set. You can see that it starts from the center, the bright parts show the finite numbers, and as the numbers extend outwards, you can see the darker parts manifest how numbers moved towards infinity, as you can see from here. So in the following slides, I'm going to show you where one can see fractals. Here are some examples in the nature. This is a tree. In a tree, the trunk is the origin of the fractal. As the tree grows taller and taller, the branches and the twigs grow proportionately into smaller versions of the whole shape. So you can see that this is the example of fractal. And then here, this is a snowflake. The fractal starts from the center. And the snowflakes looks actually very complicated, but you can see that the crystal expand outwards into different directions. As one zoom in, one can be amazed by how smaller repetitions can be. And basically you can see that the central idea is quite simple, but the whole shape is amazingly beautiful and complicated. Lightning is another intriguing example to see the power of nature. Lightning starts from electricity passing through a medium. When the medium does not conduct electricity well, for example, the air, the pattern becomes fragmented and then finally fractals. As you can see that there is great similarity between lightning and a tree in terms of fractal formation. There are many examples of fractals in math, and here I want to share 3 of them. So here, the geometric fragmentation is visually obvious and engaging. As you can see that here we have regular polygons, and then the shapes become more and more fragmented, more like fractals. And this one here, even in data analysis or sorting, one can see the concept of repetition or self-similarity. Well, it doesn't really look like, fractals here geometrically, but you can see the idea of self-similarity here among those different layers. And then here, this is called Snowflake, and I found a really interesting animated version for that. Okay, I'm not going to play the whole video, but you've got what I want to express. So it extends forever. The code Snowflake was first described by a Swedish mathematician Helga von Hoek in his 1904 paper. It was way much earlier than um, Mandelbrot created the term fractals. Now let's go back to the nature. It's amazingly beautiful to see fractals even exist in geography. So here you can see one example of water distribution. As water moves from the mountains to rivers, to the streams, and eventually into the sea, one can see numerous fractals or fragmentations, self-similarity in display. Likewise, the water distribution shapes the land, the terrain. So you can see from here. And a good example is when it comes to measuring how rough the coastline is, the more fractals are there, the rougher the coastline is. Now let's move inwards to our bodies. Fractals are seen in circulatory and respiratory systems, not only in human bodies but also in animal bodies. So here is our heart, here is our lungs, and you can see that fractals start from the trunk of these two organs, and fractals extend into numerous branches, just like a tree. What's more interesting in my research? Well, fractals are not only visibly intriguing, it can also be represented through sound. And here's a project of computerized sound. So you can see that that's the Mandelbrot set, and for each point here, a sound or a pitch is associated with that. Which is quite interesting because it can be played like an instrument. And you can zoom in forever. Okay, again, I'm not going to play for the whole recording. I need to say though, it's not really pleasant to my classically trained ears, but you will be really amazed by how modern technology has been extending our imagination of mathematics. Well, one can argue that fractals were even applied in various fields even before the term was created, especially through this famous artwork. So it was the great wave of Kanagawa, painted by this Japanese painter Kazushika Hokusai. And you can see that it was completed in the early 1800s, but the fractal concept of self-similarity is very obvious in his representation of the waves. Okay, I'm getting to the end of my presentation, and here I want to show you some engaging classroom activities. So this is the website of Fractal Foundation. As you can see that there's tons of explorations and some videos here. to show you how to engage further with fractals. And here I want to show you one of them. It's called Fractal Trees, because it's appealing and just simple to me. And then as you scroll down to the bottom of the web page, you can see further instructions for teachers and the worksheet for students. So I think this is a suitable activity for middle schoolers especially because, like I said, it's simple and it helps middle schoolers to explore trees and their fractal properties. It helps them to measure angles and length with proper tools, for example, rulers and protractors. You can see that that's the tree image that I included from the worksheet. And eventually, it helps the middle schoolers to apply quotients and ratios to real-life contexts. So I'm excited about sharing this activity with my middle schoolers very soon, and I'm looking forward to hearing what they will respond to that. These are my references for this presentation. I highly recommend the first one, a video titled Fractals Are Typically Not Self-Similar, and it comes from 3 Blue 1 Brown, this famous YouTube channel, because this video visualizes some unique features and applications of fractals, and also the host himself. He kind of holds some counter-arguments to our common beliefs in fractals. So I highly recommend this one for everyone. Thank you for listening to my presentation. I will see you next time.